December 21st, 1944. The frozen forests south of Malmedy, Belgium. A German soldier crouched in his foxhole as American artillery began its morning barrage. He had survived 3 years of war on the Eastern Front, witnessed the destruction of entire divisions at Kursk, and endured countless bombardments. Nothing had prepared him for this. The shells were exploding above his head, not impacting the ground as they should, but detonating in mid-air with surgical precision, 20 to 30 feet above the snow-covered earth, showering down a lethal rain of shrapnel that turned his foxhole into a death trap rather than a sanctuary. Weber pressed himself flat against the frozen dirt, feeling the hot fragments whistle past his helmet, watching men around him torn apart by steel that seemed to come from everywhere at once. That morning, examining an unexploded American shell in the pre-dawn darkness, Weber had seen something that defied his understanding of what was possible. The shell's nose fuse contained what appeared to be a complete radio transmitter, roughly the size of a wine bottle, packed with miniature glass vacuum tubes. These delicate components had somehow survived being fired from a gun at forces that should have pulverized them into powder. Wehrmacht engineers had spent a decade concluding such a device was theoretically impossible. The Americans had not only built it, but were manufacturing them by the tens of thousands. This single realization would fundamentally alter German understanding of what America was capable of producing, and by extension what Germany was facing. The story of how German soldiers came to witness and fear the proximity fuse began not in the forests of Belgium, but in the laboratories and factories of the United States, where in the summer of 1940, a group of American scientists were tasked with solving what every major power had concluded was an impossible problem. The National Defense Research Committee, formed on June 27, 1940, brought together leading American physicists and engineers under the direction of Vannevar Bush. Among them was Merle Tuve, a physicist whose brilliant but volatile temperament would drive a team that eventually numbered over 1,000 scientists and engineers. The problem they faced was straightforward to state but seemingly impossible to solve. German and Japanese aircraft were decimating Allied ships and ground forces. Conventional anti-aircraft guns required either a direct hit, which was extraordinarily difficult against a maneuvering target travelling at 300 miles per hour, or a timed fuse set to explode at a predetermined altitude. In practice, at the start of the war, it required approximately 20,000 shells to down a single enemy aircraft. Some estimates ranged as high as 100,000 rounds per kill. The concept of a proximity fuse had been considered for decades. Make a fuse that could detect when it approached a target and detonate automatically. Simple in theory, impossible in practice given the technology of the 1930s. Germany had explored proximity fuses as early as 1930, developing over 30 different designs, including acoustic sensors that would trigger on engine noise and electrostatic detectors that would respond to charged aircraft surfaces. By 1939, German researchers had concluded the technical challenges were insurmountable. Hitler's leadership issued directives in 1940 prioritizing projects that could reach production within 6 months to support the coming invasion of the Soviet Union. Germany's proximity fuse programs were among the casualties, though Rheinmetall Borsig would resume limited work in 1944, far too late to affect the war's outcome. The British had reached further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a small Doppler radar system. They tested prototypes on rockets, which faced far less severe acceleration than gun-fired shells. But Britain's program was stymied by 2 critical obstacles. The cost was astronomical, and Britain's industrial capacity was already stretched to breaking. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available, those used in hearing aids, were still far too delicate to survive the violent acceleration of being fired from a gun. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate, The British shared their research through the Tizard mission when America entered the war, but it would be American scientists and American industry that actually made it work. The Americans took the British research and did what no other nation could. They actually built it. Not a laboratory curiosity, but a mass-produced weapon that could be manufactured by the millions. Tuvey's Section T, at what became the Applied Physics Laboratory of Johns Hopkins University, established on March 10, 1942, in a rented Chevrolet garage in Silver Spring, Maryland, settled on a radio-based proximity fuse using Doppler radar principles. A miniature transmitter in the nose of the shell would emit radio waves at approximately 180 to 220 MHz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect. When the reflected signal reached a predetermined frequency, indicating the target was within lethal range, an electrical circuit would close and detonate the shell. The theory was elegant. Making it work was another matter entirely. Consider the engineering challenges. The fuse had to fit into the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this space, engineers had to fit a complete radio transmitter and receiver, a power source, safety mechanisms, and a detonator. All of this had to function in extreme temperatures and survive storage for months. Most daunting of all, it had to withstand the shock of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity. Every component experiences a crushing force equivalent to being hit by a sledgehammer. The shell then spins at 25,000 revolutions per minute as it passes through the rifled barrel. And after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942 as a founding member, faced the task of developing what the team called rugged vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had developed for hearing aids. These were designed for the gentle environment of sitting in someone's pocket, not the violence of artillery fire. Working with Sylvania Company engineers, Van Allen redesigned the tubes from first principles. The glass envelopes were thickened and carefully annealed. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections. The tubes were potted in wax inside the fuse body, which cushioned them against shock. Every aspect was tested by firing complete fuses from a vertical gun into the ground at the Naval Proving Grounds in Dahlgren, Virginia. The soft earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see what had broken. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up. And they were right. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge among many. The fuse needed a power source. Conventional batteries were too large and had limited shelf life, particularly in tropical heat. Engineers developed a reserve battery that used a liquid electrolyte kept separate from the battery plates until activation. When the shell was fired, centrifugal force spun the electrolyte into contact with the plates, generating electricity. This gave the batteries indefinite storage life. The fuse needed multiple safety mechanisms. It could not arm until well clear of the gun. It required protection against accidental detonation from radio interference or the ship's own radar. It needed wave suppression circuitry to prevent premature detonation when fired at low angles over water. Each safety feature added complexity. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft. Using conventional ammunition, downing these maneuvering drones typically required dozens of shots. Cleveland's gunners, firing proximity-fused shells, destroyed all 3 drones with just 4 bursts on the first day of testing. The Navy immediately cancelled the remainder of the scheduled tests and ordered mass production to begin. 5 companies were selected to manufacture the fuses: Crossley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Production started slowly. By the end of 1942, factories were producing 500 fuses per day. But American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. Over the course of the war, American industry produced more than 22 million proximity fuses at a cost exceeding $1 billion 1940s dollars. More than 100 factories participated in some phase of production. The Crossley Corporation in Cincinnati alone produced 5,205,913 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously, 7 days a week, achieving peak output of 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts produced even more, manufacturing 5,683,032 fuses, while also producing 95% of all miniature vacuum tubes used across the program. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. Workers signed secrecy oaths and were searched entering and leaving the facilities. They did not know what they were building. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The very existence of the fuse was classified. Even its use in combat was initially restricted to situations where there was no chance of a dud falling into enemy hands. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. 4 Japanese Aichi D-3A dive bombers attacked a U.S. Navy task force. As the aircraft broke off their attack, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired 3 salvos of proximity-fused shells at the departing bombers. All 3 shells exploded near one of the aircraft, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens of conventional shells. They had downed an enemy aircraft without scoring a direct hit. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. Admiral Arleigh Burke, later Chief of Naval Operations, recalled that when he served as Chief of Staff to Admiral Mark Mitscher commanding the fast carrier task forces, proximity fuses knocked down enemy planes by the dozens. The true effectiveness was demonstrated in a kamikaze attack on May 11, 1945, off Okinawa. 2 destroyers, USS Hadley and USS Evans, came under assault from approximately 150 Japanese aircraft during Operation Kikusui No. 6, many loaded with explosives and intent on suicide runs. During approximately 1 hour and 25 minutes of intense combat, the 2 destroyers and 4 support craft faced overwhelming odds. Hadley knocked down 23 enemy planes before being hit by 1 bomb, 3 kamikazes, and 1 Oka rocket bomb. Evans accounted for additional aircraft before being hit 4 times by suicide planes and left dead in the water. Both ships survived despite catastrophic damage. The verdict on proximity-fused ammunition in this action was indispensable, but for most of the war, the Pentagon strictly forbade use of the fuse over land. The risk was too great that a dud shell would fall into enemy hands. German or Japanese engineers might reverse engineer the technology or develop countermeasures. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated, bomber losses could increase by 300%. The strategic air campaign might become impossible, so the fuses were used only over water, where dud shells would sink beyond enemy reach. When a dud proximity-fused shell landed on Sicily during the invasion in July 1943, headquarters dispatched a special patrol to recover it before German forces could find it. This absolute security restriction began to crack in June 1944, when Germany unleashed the V-1 flying bomb against London. Launched from sites across the English Channel, the V-1s approached at speeds of 400 miles per hour, faster than many Allied fighters. Small, fast, and arriving without warning, they were extraordinarily difficult to intercept. From June to late August 1944, Germany launched over 9,000 V-1s against Britain. The pilotless missiles inflicted tens of thousands of civilian casualties. British defences initially could destroy only 17% of the V-1s that entered the coastal gunbelt. The situation was desperate. Prime Minister Winston Churchill authorised use of proximity fuses in anti-aircraft guns defending Britain. Modified fuses were rushed into production specifically calibrated for the small, fast V-1s. British and American anti-aircraft guns along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar systems and fire control computers. The effect was dramatic. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August, 82% of incoming V-1s were shot down. Churchill later stated that the proximity fuse made possible the successes that anti-aircraft command was obtaining. The V-1 campaign demonstrated beyond doubt that the proximity fuse was war-winning technology, but it also meant the secret was partially compromised. Thousands of fuses were being fired over land. The risk that seemed so unacceptable in 1943 now had to be weighed against military necessity. In December 1944, that calculation changed completely. On the morning of December 16, 1944, more than 200,000 German troops and nearly 1,000 tanks launched Operation Watch on the Rhine, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, aiming to split the Allied armies and capture the vital port of Antwerp. The offensive took the Allies by complete surprise. Within days, German forces had driven a bulge 50 miles deep into Allied lines. The weather was terrible, with heavy snow and thick clouds that grounded Allied air power. German commanders felt safe from artillery fire because poor visibility made accurate observation nearly impossible. They were wrong. On December 16th, the same day the offensive began, Colonel Oscar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had just received a new type of ammunition, proximity-fused shells codenamed POSIT. But Supreme Commander Dwight Eisenhower had not yet authorized their use over land. The secrecy restrictions were still technically in place. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. For the first time in the European theatre, American artillery was firing air bursts with perfect consistency, regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. Foxholes provided no protection. The shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. They could not hear the shells approaching due to the high velocity. The first warning was the explosion overhead. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton later wrote to the War Department describing an action near the Sauer River. His Third Army had caught a German battalion attempting to cross with a concentrated barrage of proximity-fused shells. By actual count, 702 enemy soldiers were killed. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. He added with evident satisfaction, "I am glad that you all thought of it first." The morning of December 21st saw proximity fuses used in defence of Malmedy itself. SS Colonel Otto Skorsenny's Panzer Brigade 150, part of the elaborate German deception operation, attacked the town at approximately 4:30 in the morning. American artillery battalions supporting the defence fired proximity-fused shells with devastating effect. The airbursts so unnerved the attackers that some charged directly into American positions, seeking any shelter from the overhead explosions. The attack was repelled by afternoon. German prisoners of war interviewed by American intelligence officers captured the psychological impact. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on the implications for air defence. If Germany had possessed proximity fuses, he estimated, the Allied strategic bombing campaign would have become unsustainable. At loss rates of 15 to 20% per mission, the combined bomber offensive would have ground to a halt. But, he immediately added, Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match. The Battle of the Bulge demonstrated how American doctrine had evolved to maximize the fuse's effectiveness. Forward observers called down fire not just on visible targets, but on suspected positions. Artillery batteries laid down barrage patterns covering entire areas. The proximity fuses meant that every shell was an effective airburst. German tactical doctrine, developed over years of warfare, had to be completely rewritten. Traditional defensive positions were suddenly death traps. Moving in the open during artillery fire was suicide. The Germans tried to adapt by dispersing more widely and staying constantly on the move. But adaptation had limits. The proximity fuse fundamentally altered the equation. German soldiers began to exhibit what American intelligence termed artillery shock syndrome, a condition specifically triggered by the helplessness of facing proximity-fused fire. Some units experienced discipline problems, with soldiers refusing orders to move into areas under American artillery coverage. American intelligence reports noted that German commanders were offering rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. By January 1945, Wright Field in Ohio had developed electronic countermeasure systems designed to jam the fuse's radio signals, based on the assumption that captured fuses would lead to German jamming efforts. But German engineers never recognized what they had captured. Having concluded that radio-based proximity fuses were impossible given artillery acceleration forces, they never fully grasped that miniature radio transmitters were inside every shell. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impassable barrier. Ground combat intensified as well. During the Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity fuses set to detonate at rooftop level showered entire city blocks with shrapnel, making defensive positions untenable. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have been successful, have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defences equipped with proximity fuses might have made D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. The technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch. Rheinmetall-Borsig developed an electrostatic fuse using capacitive detection. There were optical fuses, magnetic fuses, and experimental radio fuses similar to the American design. But none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired. But by then it was far too late. Germany lacked the industrial capacity to set up mass production. Even if production facilities could have been established, the resources required would have competed with production of tanks, aircraft, and basic ammunition. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The proximity fuse alone consumed over $1 billion 1940s dollars. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, and maintaining absolute secrecy around the entire program. The production statistics were staggering. At peak output, American factories were producing 70,000 fuses per day. That represents nearly 3 billion individual components manufactured to precise specifications, assembled, tested, and shipped to combat theatres around the world. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased efficiency, and economies of scale. At $18 per fuse, the weapon was expensive but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect. Since the shell itself cost the same regardless of fuse type, Paying extra for a fuse that multiplied effectiveness was an obvious value. The secrecy was so complete that production workers at different factories did not know other facilities were building the same components. Suppliers manufactured parts without understanding their purpose. The security classification remained in force until September 1945, when the war ended and the proximity fuse was finally revealed to the public. For German prisoners of war who witnessed the defence against V-1 flying bombs while held in Britain, the revelation of what they had faced was profound. They could see anti-aircraft guns firing and V-1s exploding in mid-air. They understood that the same technology that had devastated their forces in the Ardennes was now protecting British cities. The psychological impact was similar to what German prisoners held in America experienced witnessing American industrial production. It was a realization that they had been fighting an enemy with resources so vast that German efforts could never match them. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war, not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century with outdated assumptions about what was possible. The proximity fuse demonstrated multiple technological advances. Miniaturized vacuum tubes required breakthroughs in materials science, particularly in glass composition and annealing techniques. The printed circuit boards were among the first mass-produced examples of a technology that would revolutionize electronics. The reserve battery design using centrifugal activation was innovative. The radio circuitry was elegant and efficient. But perhaps the most significant advance was in manufacturing and quality control. Producing millions of complex electronic devices with consistent quality required systems and processes that barely existed before the war. American industry developed statistical quality control methods, automated testing procedures, and supply chain management systems that would become foundations of modern manufacturing. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes. James Van Allen, the physicist who helped develop the rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958 and credited with discovering the Van Allen radiation belts, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. The technology transfer went beyond space exploration. Engineers who had worked on proximity fuses went on to careers in the electronics industry, bringing expertise in miniaturization, quality control, and mass production. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions. Modern weapon systems used descendants of the World War II proximity fuse. The Phoenix missile, the Standard missile family, and the Patriot surface-to-air missile all use proximity fuse based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys and operate in jamming environments. But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. Throughout the war, German soldiers experienced something that challenged their understanding more than any material factor. Despite propaganda depicting Americans as weak and sentimental, prisoners discovered American military forces showed no weakness while demonstrating unexpected humanity. Medical treatment particularly affected prisoners. German doctors worked alongside American medical staff, learning new techniques and using advanced equipment. Prisoners received operations that would have been available only to the elite in Germany. Mental health treatment, virtually unknown in the Wehrmacht, was provided to traumatized soldiers. American authorities treated attempted suicides with counseling, not punishment. Prisoners with mental breakdowns received therapy, not beatings. This humanity toward enemies revealed a confidence that came from genuine strength. By March 1945, educational programs enrolled thousands of German prisoners studying English, American history, and democratic principles. The University of Chicago provided correspondence courses. Prisoners who had arrived as committed Nazis were writing essays about democratic reconstruction. Officers who had sworn oaths to Hitler were planning how to implement American agricultural methods in post-war Germany. The transformation was so complete that American authorities worried about prisoners being too enthusiastic about American ways. Some requested to stay in America after the war. Between 1945 and 1946, over 370,000 German prisoners were repatriated from American camps. They returned to a Germany divided, destroyed, and destitute. But they brought with them knowledge of how a democratic industrial society functioned. Many former prisoners rose to prominence in West Germany's reconstruction, bringing American methods to German industry and American democratic ideals to German politics. The broader lesson extended beyond the proximity fuse to the entire character of American military production during World War II. America outproduced the Axis powers not just in quantity, but in quality and sophistication. American weapons were not always individually superior, but American weapons worked reliably, were produced in overwhelming numbers, and included technological innovations like proximity fuses that gave critical advantages. The combination of quantity and quality was what made American production decisive. The proximity fuse provided a force multiplier that turned numerical superiority into overwhelming dominance. By the final year of the war, German forces were facing enemies who had better weapons, more weapons, and technological advantages that made traditional tactics obsolete. The casualty statistics reflected the impact. During the Battle of the Bulge, despite initial surprise and favourable terrain, German forces suffered disproportionate casualties. American artillery was responsible for an unusually high percentage of German losses. Medical personnel reported that wounds from proximity-fused shells tended to be more severe than wounds from traditional artillery. The shrapnel came from above, targeting the head and shoulders. Multiple fragment wounds were common. The lethality was significantly higher. By March 1945, as Allied forces prepared to cross the Rhine and advance into Germany, proximity-fused ammunition had become standard for all American artillery. Factories were producing fuses faster than they could be shipped to Europe. The Germans never developed effective countermeasures. Electronic jamming was theoretically possible but required understanding the fuse's operating frequency and characteristics. Without intact working fuses to analyze, German engineers could not determine specifications needed for jamming. Even if they had, deploying jammers across every potential target would have been impossible. Physical countermeasures were equally ineffective. The fuses operated by detecting reflected radio waves. Reducing the radar cross-section of troops and equipment was impossible. The human body itself reflected enough energy to trigger the fuse at close range. The only defense was dispersion, spreading forces widely enough that a single shell would not catch multiple targets. But dispersion reduced combat effectiveness and made coordinated operations difficult. German tactical doctrine had evolved around concentrated formations. Dispersing to counter proximity fuses weakened overall capability even as it reduced casualties. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted. The sense of helplessness broke the will to resist. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. This was psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated futility of resistance. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war. Estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns and increasing effectiveness of defensive operations. Against kamikaze attacks in the Pacific, proximity fuses were credited with preventing ship losses that would have significantly delayed operations. The strategic impact was multiplied by production scale. Because fuses were available in unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated. Defensive fire plans could cover vast areas with overlapping patterns. The psychological effect of this abundance was as significant as the physical effect. The technological legacy of the proximity fuse extended far beyond military applications. The miniaturization techniques influenced the entire electronics industry. The quality control methods became standard practice in manufacturing. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training and supervision. These lessons shaped post-war American industry. The space program, the development of computers, and the transistor revolution all drew on knowledge and techniques developed during the proximity fuse program. The scientists and engineers who worked on the fuse went on to distinguished careers. James Van Allen became one of the founding figures of space science. Merle Tuve continued leading scientific research at the Carnegie Institution. Dozens of others joined universities, industrial laboratories, and government research facilities, bringing expertise in miniaturization, electronics, and systems engineering. The intellectual capital developed during the proximity fuse program helped establish American leadership in electronics and technology throughout the second half of the 20th century. The industrial infrastructure created for fuse production found new uses after the war. Factories that had manufactured vacuum tubes converted to producing television tubes and consumer electronics. Workers trained in precision assembly became the workforce for the emerging electronics industry. Supply chains established for fuse components supported the growth of consumer electronics markets. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons like jet aircraft and ballistic missiles. These were impressive achievements, but came too late and in too few numbers to affect the war's outcome. America invested in technologies that could be mass-produced immediately. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability. The result was a weapon available in overwhelming numbers when needed. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would offset Allied numerical superiority. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The proximity fuse was not a superweapon. It was a very good weapon produced in very large numbers. That approach proved decisive. In the final accounting, the proximity fuse represented everything that made American industrial power dominant in World War II. It combined advanced technology with practical engineering. It required massive investment but produced proportionate results. It was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable. It was a perfect example of how America fought and won World War II, by solving impossible problems through the application of extraordinary resources, brilliant engineering, and an industrial base that could produce technological miracles by the millions. The German soldiers who faced proximity-fused fire understood this implicitly. Wehrmacht veterans interviewed after the war consistently described the fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy with capabilities beyond their ability to match or counter. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. The weapon that had seemed impossible to build became the weapon that changed warfare. American scientists, engineers, factory workers, and military personnel had accomplished what the world's experts declared could not be done. They had miniaturized complex electronics, made delicate vacuum tubes survive artillery forces, and manufactured the result by the tens of millions. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that the greatest victories come not from seeking the impossible, but from making the necessary possible through sheer force of will and unlimited application of resources.